During this presentation, we have to discuss the experimental determination of thermal conductivity of a good conductor. For that, we use Forbe's method. Forbe's method is used to determine the thermal conductivity of different metals. Consider a metal in the form of a long rod. The metal is having uniform area of cross section. The one end of the rod is heated using steam. The different thermometers placed at different positions on the surface of the rod will give the temperature of the rod at different points. Once the rod has reached a steady temperature, the quantity of heat energy crossing the point B in unit time is given by the relation Ka into d theta by dx at the point B. We may arrive this value from our basic definition. We know that quantity of heat energy passing through the specimen is directly proportional to area of cross section, directly proportional to temperature difference, directly proportional to time, and inversely proportional to distance. Now combine all this, you may get Q is proportional to A theta 1 minus theta 2 into T by X. To remove the property sign, we have to introduce a constant K called the coefficient of thermal conductivity. Therefore, Q equal to K A into theta 1 minus theta 2 by X into T. But theta 1 minus theta 2 by X equal to d theta by dx called the temperature gradient. The rate of loss of temperature with respect to distance is called temperature gradient. Now the equation becomes Q equal to Ka d theta by dx into T. If T equal to 1 second, then the quantity of flow is Ka into d theta by dx. In this way, we have arrived at this relation. Once the point B is having this much heat energy, the quantity of heat energy lost by the rod between the points existing P and C is given by the equation integral B to C rho A dx into S into d theta by dt. The heat energy is lost in the form of radiation. The amount of heat energy radiated between B and C is given by this equation. How do you arrive this equation is the next question. We know that heat capacity H equal to ms into theta. Here m is equal to mass, S the specific heat, then the rate of change of temperature is d theta by dt. We do not know the mass of the rod. We may estimate the mass using the formula density equal to mass by volume. Then mass equal to rho into V. But V equal to area of cross section into dx. Therefore, m equal to A rho dx. Then H equal to A rho dx S into d theta by dt. In this way, we have arrived this relation. Now, the quantity of heat energy crossing the point B in unit time should equal the amount of heat energy radiated between the points B and C. Here, we may cancel A since it is present on both sides. Then the value of K equal to the integral rho S d theta by dt into dx whole divided by d theta by dx at the point B. This is the value of K. Now the numerator and the denominator are estimated by performing the experiment. The entire experiment is divided into two parts. One is static part and the other is dynamic part. I will go to the static part. In the case of static part, the experimental rod is heated for at least 6 hours. Once the steady state is reached, measure the temperatures from the thermometers inserted at different points. Now a graph is drawn by taking the temperature on the y-axis and distance from the hot end on the x-axis. It's a decay curve. Say x values on the x-axis, theta values on the y-axis. It is a decay curve. Now a tangent is drawn to this curve and the tangent is allowed to meet the x-axis. From the point B, a line is made and it's allowed to meet the tangent at the point B. Here, this is the angle alpha. This is a right triangle. This is 90 degree. So the opposite face is hypotenuse. From this sine alpha equal to opposite side to this angle alpha is BP divided by hypotenuse PC. Then cos alpha is equal to adjacent side BC divided by hypotenuse BC. Sin alpha by cos alpha, which is equal to tan alpha equal to BD by PC into PC by BC, which is equal to BD by BC. The value of BP, not BD, this is P. We have specified this one as P. BP, this is BP. The value of BP is d theta. Then the value of BC is dx. Sin alpha by cos alpha equal to tan alpha. Therefore, tan alpha equal to d theta by dx at constant at the point B. So, instead of d theta by dx, we have to put tan alpha. The second part is dynamic part. The given rod or rod specimen is heated until it reaches a steady state. Then the rod is allowed to cool. A thermometer is inserted in the middle of the rod, and with the help of the thermometer, we are going to measure the temperature of the rod at equal intervals. Now, the second graph is drawn, taking temperature on the y-axis and the time on the x-axis. It's also a curve. From the curve, the value of d theta by dt is measured for a particular temperature. For different temperatures, we can have the value of d theta by dt. See, this is a graph corresponding to the dynamic part. The y-axis indicates theta, different temperature values. X-axis provides time interval. If you see the curve, it is a decay curve. For a particular theta value, a tangent is drawn. For the given theta, you may get d theta by dt. With the help of the graphs 1 and 2, we can draw a third graph. In the third graph, d theta by dt values are taken along the y-axis, x values are taken along the x-axis. X stands for the position of different thermometers from the hot end. The curve is like this, and allow the curve to meet the x-axis, and from the point B, draw a line, and the line is allowed to meet this curve. Now, shade the area enclosed by the curve and the line segment. The area of the shaded portion gives the value of integral d theta by dt into dx, limit varying from b to c, that is equal to area of the shaded portion. Say this is the total area. This area corresponding to dx. Then the total area represents d theta by dt into dx, integral limit varying from b to c. Now the thermal conductivity K equal to rho into S integral b to c d theta by dt into dx divided by d theta by dx at the point B. Instead of this d theta by dt into dx, we have to put this area. This area is measured using a graph sheet, and rho, the density of the metal, which is a constant. Yes, the specific of a metal, which is also a constant. Then write down the area value divided by the value of d theta by dx is tan alpha. We obtained from the first graph. If we substitute all these values, we can get the thermal conductivity of the given metal.